Good morning, Dr. Azian. My name is Mohammed Dr. of Chandrasekhar. I would like to explain the assignment question number dB at 10 radian per second. The second question is that bandwidth 3 radian to 30 radian, and the answer is about 50 radian per second. And the third is the cutoff rate, which is negative 40 dB per decade. The B question is that the forward part transfer function of the unity feedback for inertial control system is given as follows. The first is a GS equal to K S plus 50 over S square plus 15S plus 100. So we have to draw the Bode diagram of the system for K equal to 2 using the straight line approximation and label the gain and phase margin on the diagram. So the answer is that I given is that GS equal to KS plus 50 over S square plus 15S plus 100, which is K equal to 2, and I substitute the K equal to 2, and then I open the bracket by 2 bracket 50 bracket 0.025 plus 1 over 100S bracket 0.015 square plus 0.155 plus 1, and then I cut off the equation, and the final answer I get is a 0.025 plus 1 over 5 bracket 0.015 square plus 0.155 plus 1. So the JW I get is a 0.02 JW plus 1 over JW 0.01 bracket JW square plus 0.15 JW plus 1. So the gain is equal to K equal to 1. So the simple zero will be the 0.02 JW plus 1, and the WCC is equal to 50. So the gain in the dB will be 20 log bracket 1. So the answer get is 1. So the WC square equal to 100. So the WC will be 10. Next, based on the bot plot in plot Q1b, evaluate the stability of the closed loop system. Justify your answer by estimating the value of the gain margin and phase margin. So the gain margin will be 0 minus negative 35, and the answer will get 35. And the phase margin is negative 19 minus negative 180. So the answer will get 90 degree. So both of the value of the gain margin and the phase margin is positive. So therefore the closed system is stable. And then number two question is that if the value of K is increased by 20 dB, evaluate the system stability and then justify your answer by stretching the resultant bot plot and the same graph of the plot by the question number 1b. So the gain margin will be 0 minus negative 15, and the answer will get 15 dB, and the phase margin will be negative 170 minus negative 180, and then answer will get by 10 degree. So since both of the value gain margin and phase margin are positive, therefore the system is stable but lower than the original system with this K equal to 1 dB due to the lower values of the gain and phase margin. Then I would like to explain about the plot diagram that I have to drawn. First, I drawn the gain, which is K equal to 1, and then the simple 0, which is 0.02 JW plus 1, and then the pole at the origin, and then the complex pole. After that, the negative 20 dB with the negative 60, and then the end with the negative 40 dB. The gain margin with the GM is equal to K equal to 20 dB. And then I go with the phase merger, which is same as a K equal to 20 dB. First, I will draw at the 0 degree, which is pole at the origin, and then the complex pole, and then the negative 90, and then negative 40 degree, and then the gain of the gain, which is K equal to 1, and then at the simple pole, which is 0.02 JW. That's all. Thank you.
Hello guys, today I want to discuss question 2, which is the question 2 given question is like this, which is GS, KS plus 10, S square plus 8S plus 25. So it's the original question. So we need to do some calculation until here. When then we get the new gain, which is 1.6. And then after that, we insert this formula and then new gain, which is 4.082. So I draw here. First of all, I do some of the list out the something which is the 4 step before drawing. So after that I got the 4.08, and then I drawing here, and also same to the pole at origin, which is as I draw from the 20 dB until the 1000 here, because of the 10 scale, and then multiply with 10 scale and another 10 scale, and until we get 1000 here. And to the step 3 we simple 0, then start from the 10. So from here 0 until 10 here, so we do straight line. And it also same to the complex pole, or we call is the quadratic pole. It's start from 5, so that's why we start from 0 until 5 here, and then we drawing to below, which is 50, because of 5 multiplied with the 10, and then we got 50 here. And then after that we do the plot, final plot, which is this one, the blue line, final plot here and here. And then we do the slope, calculate the slope, which is here is the negative 20 dB, here is also negative 20 dB, and here this slope is the negative 60 dB, and here slope here is the negative 40. Because of I calculate this one, I multiply with this one, which is 0 dB plus 0 dB, and then here is a negative 20 dB, so that's why I got here is negative 20 dB. And also same like another slope for the calculation. So after that I do the phase. It's also same, the method, but the difference is you when you want to start the pole, I drew the negative 19 here, so the straight line. Again you can do straight line here, but you not drawing also no problem. So after that the zero simple 10, which is start from 10, but we need to do a backward 10 times, which is here I start from here, which is 1, so that's one I straight line here. This one is the simple 0, and also same like this, the complex pole start from 5, so that's why we start from here 0.5. So this one is the complex pole, and then after 3 point we do straight line here. Okay, after that we do some calculation here. calculation gain margin. How we want to get the gain margin? We need to drawing from negative 180 straight line until we 1018 here. So until the touch the final plot, and then we go to the phase. We go to the magnitude, which is the final of the magnitude plot. Here we got here, and then until this one. So 0 minus 038. So that's why I got the gain margin is 38. After that the phase margin. Okay, the first margin, phase margin I get from here, which is start from 0 until I touch the final plotting of the magnitude, and then going down here, and then I get here. So negative 125 minus negative 118, and then I get 55. All right, so positive value. So we know that here is the stable. After that, when estimate value bandwidth when we want to calculate is here the final plot of the magnitude minus with the negative 3. Everything is negative 3. That's why I got here is the 21, something like that lah. 21, and then do pointing here, actually here, and then I estimate like estimate negative 0.155, and then the cutoff value is the final plotting of the negative 50 dB here, the slope of the magnitude dB. This is the cutoff here, and then we know that when we increasing the 30 dB, here, increasing the 30 dB. That's why I try to increasing 30 dB here from the final plot, and then increasing here. So that's why I got the new line from the plotting Bode diagram. So when increasing the k by 30 dB, which is when the Bode magnitude plot is shift outward, the system gain increase and the gain margin decrease. As the gain increase, the system become less stable and become unstable if the gain margin become negative. So
Assalamualaikum. I will explain about question 3. So from this figure 3.1 plot, for question A1, determine which system has good stability. So based on this plot, system S2 is more stable than S1 because it doesn't encycle negative 1. So for question 2, determine number of integrator of the system. From the plot, we can see that system S1 has 0 integrator and S2 has 1 because the arrow goes down to infinity. For question B, we need to find the loop transfer function of the system if gain is 10. For this, we need to do step by step, starting with first, we need to factorize the equation and change S to JW until we get this. Step 2, we need to find frequency approaching 0, where we get 0 degree, and frequency approaching infinity, and we will get negative 180. Next, we rationalize the equation and find the real and imaginary axis crossing. For real axis crossing, we get 0, and for imaginary axis crossing, we get negative 2.24, and we will get the plot like this. For question C, evaluate the closed loop system stability in terms of gain margin and phase margin. Since the plot only cross real axis at origin, the gain margin is infinity and the system is stable since both gain and phase margin are positive. For question D, evaluate the stability of the closed loop system if the integrator is added to the forward path of the system. From this new plot, the dotted line is the added integrator, which is rotated by 180 degree. The plot also doesn't cross the negative real axis, hence the addition of the integrator has reduced the system stability. That's all from me, thank you.
Hi, my name is Ng Sok Lee. My matrix number is 2311511592. So I'm going to present for questions 4. Questions 4 is to find the Nyquist diagrams. So the first question is to determine the number of integrator in S1 and S2. So for S1, it is 1 integrator since the phase lag is negative 90 degrees, and system 2 is having 2 integrators since the phase lag is negative 180 degrees based on the diagram given. And then system 2 is having the better stability since it is further away from real axis negative 1 compared to system 1. So the part B of question 4 is to draw the Nyquist plot for transfer function given GH equals to K over S squared plus 2S plus 3. And step 1 is to substitute S equals to J omega. After that, we got it, and then we just calculate for the magnitude and also the phase. Phase is equals to arctangent imaginary over real value. And step 2 is substitute the low frequency omega equals to 0 into magnitude and phase. And we also do the same for the high frequency omega equals to infinity and substitute it into the magnitude and phase. So we got the answer for omega equals to 0 is 1 over 3 and degree is 0. And high frequency, it is 0 and the degree is negative 180. So we follow by step 4 to draw a Nyquist plot is to do rationalization. We have to cancel the imaginary j from the numerator part of transfer function. After that, we let imaginary equals to 0 and real equals to 0 to find the omega. So from the calculation that I did, we got that the imaginary part omega is equal to 0 and real part omega is equal to square root 3. After that, we substitute this square root 3 into the magnitude, and then to find the imaginary axis crossing when the real axis is equals to 0. So the answer we got here is negative 0.2887. Lastly, I draft a table for easier to plot the Nyquist plot. So this is the drawing that I get, where negative 0.2887 is crossing imaginary axis and the real axis is 1 over 3. And since it is negative 180 degrees, so it starts from the second quarter and then turn 180 degrees back to quarter 1. The gain margin that we got here for this question is infinity, and since the plot is crossing imaginary axis only instead of real axis, and then before this we got that the phase margin is equal to 180 degree and the magnitude is less than 1, so it is having a good stability. We are adding an integrator, then the plot will be rotated by 90 degrees. We're adding 1 over s into the system. So the infinite gain will be observed at omega equals to 0. And then this plot that I draw is, it will start from the third quarter since it is adding 1 more integrator and then rotating 90 degrees towards infinity. And the gain margin that we got here is not equals to 0 since it is crossing real axis. And then it goes infinity 90 degrees downwards and the phase margin is 90 degrees and it is equals to less than 180 degrees. So the system has lower stability than previous. When we are adding a 0, s equals to negative 2 to the system, the effects of 0, it will pull the plot outwards and upwards. And this is the plot that I draw where it starts from the first quadrant but start with 0 at the imaginary axis and real axis, and then it will pull outwards than previous and upwards that it is greater than 1 over 3. And here we can see that it is no encirclement of negative 1, but the gain margin is increases. And also phase margin remains 180 degrees, so the stability is improved than previous.